Thanks for joining me today at this Open IoT Summit workshop. We're going to talk about some very cool, very exciting, very interesting technology, all about the Internet of Things. It's going to be all about connecting things, all about the latest and greatest technology out there. So to kick us off, I thought I'd first start off with a quick survey of where I'm at in my IoT deployment and the kinds of stuff that I've rolled out, because I think it's very cool and I'm very excited about IoT technology. So let's start with my smart connected refrigerator. This is the centerpiece of my kitchen. It is one of the most amazing gadgets I've ever seen. It's got a sensor built into the door. I put a gallon of milk on top of it. The refrigerator monitors the weight of that milk, communicates to the cloud. The cloud does some predictive analytics and figures out exactly when I'm going to run out of milk. And so today at the show this morning, actually, I got an email from this refrigerator because it's connected, it knows how to communicate. It said, hey, you're about ready to run out of milk. And I thought, awesome. I'll stop on the way home today, I'll get some milk, crisis averted. Internet technology is amazing, right? You're thinking to yourselves, that's awesome. But you know what? This refrigerator, it goes one step further. It's even got an IP camera built into it. So today at the show, if I get bored, I can open up my smartphone, I can peer into the refrigerator, see exactly what's going on, making sure all the vegetables are getting along, nobody's fighting or getting hurt. Awesome technology. This little guy, though, is my absolute favorite. I might have put this together myself, but it's an amazing product. It's my smart connected barbecue. It has the ability to email me and ask me if I feel like having a barbecue this weekend. It's awesome. Today, on the way home, I'll probably open up my phone. I'll get that thing preheated because I'll wind down when I get home today with a nice little barbecue, a glass of red wine. I absolutely love that product. This one I am not totally sure about just yet. I'm not 100% sold on this product yet. I thought, smart scale might help me get in better shape, lose a couple of pounds, that kind of stuff. But it's an absolute spam machine. It direct messages me on Twitter all the time. It emails me. It text messages me. It even endorses my LinkedIn profile from time to time. I feel like I'm being stalked in the digital world. So I'm not 100% sold on that particular product just yet. But what is my point? My point is that all of these systems are starting to connect to each other. They're talking to each other. They're communicating with each other. It's amazing technology, right? Right? Everybody out there? Amazing stuff, right? Actually, full stop. You got to be kidding me. I hope you didn't think I was going to go along and tell you about smart connected barbecues and refrigerators, because that's not what we're here to talk about. So let me reset your expectations real quick. We're not going to be talking about consumer level products here, because I think there's still a lot of people struggling to find value in these applications, like a refrigerator with an IP camera built into it. Can somebody please tell me exactly what the value is in an IP camera built into a refrigerator? I just don't see it, and I think there's a lot of people struggling with that same question. So today, we're going to talk about the Internet of Things stuff, and there's a lot of hype around it right now. You've got big data people on one side talking about how they're going to consume massive volumes of data. They're going to mash it up, they're going to analyze it, they're going to figure out how to solve incredibly complex problems, which is great. They've got systems to do that today. You've got the sensor people at the other side of the connection, and they're going to connect all kinds of instruments and sensors to things in the physical world. They're going to start generating all of this data. We'll have situational awareness of everything that's going on around us at all times, which is great. That's amazing. You know what I don't hear people talking about, though? I don't hear people talking about all of the legacy infrastructure that was shipped 10, 20, 30, 40, 50 years ago. Think about how far back we invented electricity or just moving water around in our cities. I don't hear anybody talking about how we're going to connect those systems that actually we use in society every single day. How are we going to get that stuff connected to the Internet of Things? And when we do, what kinds of problems might that solve? Problems that we might interact with every day that we don't even realize are there, that there's a solution to them. So today, without further ado, no more jokes about connected refrigerators or barbecues. My name is Matt Newton. I'm the Director of Technical Marketing for an industrial automation company, which might be different than what a lot of people else here are today. And the name of my company is Opto 22, and today I'm going to spend some time talking to you about, at least from my perspective, how I think we can actually start bridging this gap of the physical world, all the stuff that's already out there, that legacy equipment, and start bridging that gap to the digital world and figuring out how we can get there, what kinds of real world problems we can solve today. So, we're going to cover 3 key ideas today. I want everybody to walk out of here with just 3 ideas in their head. The first one is that there's a massive opportunity out there. Right now, there's all this stuff out there. Sensors, actuators, relays, transmitters, closed loop control systems, stuff that was shipped way before the internet was ever available. It wasn't designed for connectivity, but yet it's performing a task, it's functioning, it's generating data that might otherwise be useful to us if we could just get access to it and start identifying opportunities to actually solve problems. So that's idea number one. I want to try to help us get our arms around exactly what the opportunity is that I'm talking about. So then once we understand the opportunity, I'll spend a little bit of time talking about why I think we haven't gotten there yet, and some of the challenges and the hurdles that we need to get over, and how I think we're actually going to do that. And finally, I'll spend a little bit of time talking about what I think the key to getting there is, because there is one specific key, and hopefully it's at this show today, which is why I'm here. I think the key is developers. It's all about embedded Linux developers, the people that know how to take a GPIO signal in the physical world, like on a Raspberry Pi board or an Arduino board, some physical signal, make it available up in the cloud. So we're converting that analog to digital signal. I think those people know how to do that, and I think they're going to be the ones that solve this problem for us. So 3 key ideas: opportunity, how we're going to get there, and who's going to do it. All right, a few definitions, just to get us started off on the same foot so you guys know exactly what I'm talking about today. Let's start with a thing. We hear things talked about all the time in the context of Internet of Things. Well, what is the thing? And yes, I am intimately aware that you've probably seen the Nest thermostat a ton today in a lot of presentations. But you know what? That's a home run product. It's a great product. It solved a real world problem. So going back to the thing, what does it do? It does 3 important things, 3 important characteristics about this thing or device. Has the ability to sense, has the ability to communicate, has the ability to control. So when we think about our Nest thermostat, it's got sensors built into it. 2 very important sensors. It's got a temperature sensor built into it and a proximity sensor built into it. So it's monitoring the temperature in the room. It's checking to see if I'm there, if I've shown up in the room in a while. And if it realizes I'm there, it's going to communicate out to the cloud, interrogate some system up there, figure out what I like my temperature set to in my house, and then establish some type of control output in the form of a signal that gets sent to an HVAC system, a real world piece of hardware that's already out there. So remember, IoT thing, don't complicate it. 3 simple things. It senses, it communicates, and it controls. So the next definition, and I promise we're not going to do death by definition here. There's only 2 more to go here. What the heck are these legacy things, and why should you care about them? Well, legacy stuff is the existing infrastructure that's already out there today. We talked about it, the billions of systems that are already out there today. We've already paid for them. They're already performing a task. They're functioning. They're probably old, but like I said, they're still functioning. There's still some value there. We can get more value out of them. They just weren't designed to connect to the Internet of Things because the Internet hadn't been invented yet. So if we start thinking about how we can start connecting them and bridging that gap, that's what we're here to talk about today. What's the opportunity and how are we going to get there? So 3rd and final definition, a control system. This is where I live right now in the industrial automation space. You might have heard this coined as a control system or a closed loop control system. Again, don't complicate it. Think about your car when you're driving down the road. You're on the freeway, you hit 70 miles per hour or whatever speed you're comfortable at. You push that button on the side of the steering wheel, which is your set point, the speed that the car is going to travel. And then the computer on the car takes over from there and actually checks things in the real world, like how fast those wheels are spinning or the axle is spinning. And then if we get outside of that set point range, that 70 miles per hour, we apply the gas pedal or we apply the brake. That's the control system taking over, running, doing what it's supposed to for your cruise control system. Typically, you're going to find this stuff in industrial automation applications or large pieces of equipment, the world where I live in right now. All right, definitions out of the way, hard work's out of the way. Hopefully, we're all on the same page at this point about those 3 things. So going back to the cool stuff, the fun stuff, the stuff that I'm passionate about, the Internet of Things stuff, there's a ton of hype around it. Everybody's talking about it in the media cycle. There's a lot of naysayers trying to figure out where's the real value in it. I mean, if you look at the Nest thermostat, that was a home run. But Google's having trouble right now trying to figure out, how do I get another product out of these guys? How do we ship another product that's going to solve a problem? The reason for that is that these are greenfield products. These were designed from the ground up to solve a problem that someone identified, and they used internet connectivity to do it. That means these systems came with things like embedded Linux built into them. It's got a full-blown TCP/IP stack built into it. And the clever folks that designed this stuff, they knew that internet security was going to be important. So it's got SSL encryption built into it, authentication, all the stuff we're familiar with today with internet security. What's the common theme with all this stuff though? It was designed very recently. If we're thinking about our legacy infrastructure, it was never designed with that stuff in mind. It was never designed for security or internet communication. So mostly in the consumer space right now, but I personally think there's a massive opportunity out there that we haven't quite grasped yet, or we haven't quite figured out how to solve the problem. So what is that opportunity I keep talking about? I keep mentioning these billions of things and all of our infrastructure and how we're going to start being able to connect them. What if we did start actually connecting all of that stuff to the Internet of Things? And we're going to talk more about what problems we might solve there, but think about it. All that stuff out there, generating all that data. Remember, it all runs on data. Data helps us figure out problems. How do we get access to that data and start figuring out problems, solving problems, all that kind of stuff? So let me walk you through a quick application story that a company I'm aware of went through. It's actually a pretty cool story. Now, if you take a trip in time with me, back about 60 years to when my dad was a little kid, and he'd go outside, he'd run around all day, he'd play, he'd climb fences, he'd get into trouble, just generally acting like a maniac of a little kid, right? He'd get home at night, and back then, if he sat down for a while, he could really feel his lungs burning. They were literally burning from all the smog and pollution that he had breathed in during the day. Because we had a serious problem with air pollution back then, massive problem. But the good news is the state has actually gotten smart about it. And about 20 or 30 years ago, we started rolling out all of these green energy sources. So we've got the hydroelectric dams going in everywhere. We've got solar or wind turbines out there in the California desert generating all kinds of electricity. And everybody here knows how fast solar is rolling out. You get a call at least once a week from some telemarketer saying, would you like to buy solar from me? So it's great. We've cleaned up the environment. We can go out and breathe again. Kids are safe. But these green energy sources are actually fairly new technology. So there's still a few bugs, a few hiccups we've got to figure out how to solve. One is that they're not always available. They're based on nature. Nature's not predictable, which means our energy sources are not predictable. The other problem is that they're not always needed. We've ramped up the rollout of this infrastructure so quickly that we're actually generating more electricity during the day than we need, which is a serious problem for the grid. Because if the grid gets out of whack, too much power, too little power, we have a problem. The third problem is related to that second problem. We generate more electricity than we need. What do we do with it? Our grid was not designed to store power. Our grid was designed to transmit power. So we've got this extra power, we don't know what to do with it. That's what Elon Musk is trying to figure out with that Tesla Powerwall thing. It's a giant battery to save all that solar electricity and maybe sell it back to the utility or do something useful with it at a later purpose. So going back to our grid, it's fragile. It's very fragile. If we send just a little bit too much power to it, it's very similar to like a Raspberry Pi or any other electronic device. You put too much power in, what happens? It melts or it blows up. Same kind of problem on the grid, but we're moving around a lot more electrons, so the problem gets substantially larger. Now the flip side to that is that if we don't send enough power to the grid, we run into the things that we're all familiar with. Blackouts and brownouts. They happen in California more often than in other places because we have this variable green grid system. So remember, the grid is actually a fragile system. The real crux of the problem in California specifically is that our demand changes throughout the day. We start off at a pretty even keel there, but then we go to work and we leave our houses, we turn off our appliances, our lights, demand drops. We're all cooped up in our offices, writing some code somewhere, trying to figure out the next genius idea. But the scary thing happens when we go home in the afternoon or the evening and we start turning on all of our appliances, and in a very short amount of time, demand spikes dramatically. We have these peak events. Now in California, I don't know that most people have heard of this, but this is a real problem. And our utilities have coined this clever name for it, the California duck curve. Because if you look at it, it kind of looks like the back of a very sweet, cute little duck. But I assure you, this is not a sweet, cute little problem. If you think about how much power we're getting from our grid today, 19, 20%, we're scheduled to ramp that up to 40% in the next few years. And so there's a ton of really smart people trying to figure out what we're going to do about this and how we're going to solve that problem. So what do we do right now when we don't have enough electricity? Our utilities get on the phone to our energy producers who are natural gas power plants, our nuclear power plants, and they say, we're in trouble, we don't have enough juice, ramp up production as fast as you can because we're going to have a problem very shortly. Now, the problem with that is that those plants right there, they take about 24 hours to spin up or 24 hours to spin down. So it's not like we can just get on the phone and say, hey, throw another power plant at this problem immediately and fix it. It's not that easy. So what we do instead, we curtail different energy sources. Curtailment is when we disconnect an energy source. So it's a lot easier to disconnect a bunch of wind turbines and solar panels than it is to ramp down an entire nuclear power plant like that. So guess who gets curtailed most often? Our green energy sources, which is a bummer, right? Because then we're not getting our energy from a green source. Maybe we're polluting the environment further. We're kind of missing the point there. So who's trying to figure it out? Because it's a really serious, complex problem. In California, it's somebody called CAISO. It's the California Independent Systems Operator. Now, you might think the utility is a bad guy, but these guys actually have a really demanding, really difficult job because they're trying to solve this problem. So what do? They look at all kinds of data sources. They're looking at weather reports. They're looking at historical demand reports. They're essentially trying to predict the future. How much energy am I going to need tomorrow? Which of these power plants do I already have spun up? Which ones do I need to spin down? Is it going to be sunny? How much power can I count on from my green sources? It's a constant moving problem that they always have to figure out every single day. Because remember, the electricity market is just like any other market, right? Supply goes up, demand goes up. We try to reach equilibrium in the middle, which is how much power the grid needs in this case. So if you remember your economics classes, how do we handle pricing in a market? We have a market price. Utilities do the same thing. They just call it the spot price of electricity. Now, it's a little bit different than a typical market price in that it fluctuates minute by minute, up and down, up and down. And what they're doing there is they're trying to incentivize or penalize our green energy producers. So they're saying, if there are times when we really don't need energy, I'm actually going to fine you, like $300 per kilowatt hour. Massive fines, tens of thousands of dollars per day if we don't figure out how to get that electricity off the grid. But the flip side to that is there's an opportunity to make a ton of money there because it'll range all the way up to $300 or $400 per kilowatt hour. But what are these green energy producers going to do? Because it's moving all over the place all day. Remember, our legacy infrastructure, our turbines, this stuff rolled out 20, 30, 40 years ago, way before the Internet of Things. We didn't conceive of the duck curve problem back then. It doesn't have connectivity built into it. So today, what does our poor operator do? When there's a curtailment event or an opportunity to make money, he jumps in his truck, he drives around from turbine to turbine, gets to each individual turbine, and manually turns it off. He manually turns off this old legacy equipment. Now that's a manual process, so it's failure prone, right? Maybe even probably definitely inefficient. I don't want to spend my time driving around from turbine to turbine, as beautiful as the scenery looks there. So what are these green energy operators supposed to do? Imagine yesterday, you're a wind turbine operator, you own a farm, you got 5 or 6 turbines out there. Yesterday your truck broke down during a curtailment event. You didn't have time to get there and you got slammed with tens of thousands of dollars in fines. Kind of a bummer. And you're thinking, well, tonight it's supposed to be windy, there's a thunderstorm coming in, it's going to blow into the turbines, maybe I'll be able to make my money back. So you're waiting up, you're excited, you're in trouble, you're out a bunch of money from yesterday. Waiting up at about 3:10, the utility contacts you and says, throttle back your energy production, demand is way low because everybody is asleep, we don't need the energy from your sources right now. So what do? You've got no Wi-Fi to get to this thing. There's no cloud or big data around when we design these systems. They don't have a digital on-off switch. They're designed to be controlled from the physical world. That's a problem for these folks. Now I want to go back for just a minute because I know we've talked about legacy infrastructure and I'm probably boring you with that right now. But what is an Internet of Things device? It senses, it communicates, it controls. So if you think about our turbine, what is our wind turbine? It's got a control system built into it. A control system is monitoring things like the wind speed, the wind direction, and it's setting outputs on the turbine, like moving the head around to get it shifted into the wind just right so that we try to get the most money we can out of it. So it's doing some sensing and some controlling. But what is it missing? The most critical part, it's missing communication. Has no way out to the Internet of Things. So the question I'm trying to get to here, the point of my presentation is, What would happen if this stuff started joining the Internet of Things? What would happen if all of that legacy stuff out there today could peer into the digital world? For example, with our turbines, what would happen if those turbines could look at a website, figure out what the spot price of electricity is, and automatically turn themselves on or off? If I was an operator, that's instant value for me, because now I don't have to drive around at 3 in the morning turning my turbines on and off. And hopefully there's an opportunity there for me to lower my costs and increase my profit. And that's exactly what this company did. They actually built their own Linux-based embedded Linux analytics package. They host it up in a cloud somewhere, and it sucks in a whole bunch of data from all these control systems on the turbines. So it's looking at like wind speed and how profitable the turbine was last year and its maintenance costs and how often it's going down, and it's looking at the spot price of electricity, and it's doing a data mashup on it. It's putting all of that information together and figuring out, this is when I can be profitable. This is when I need to turn on. This is when I need to schedule my service call because it looks like something's about to break. The turbines have become intelligent at this point. They're connected, they're communicating, they're an IoT device. And that is the real Internet of Things, if you ask me. It's not about IP cameras in refrigerators or smart connected barbecues. These are real world problems that we can solve if we get access to these systems' data and start thinking about things just a little bit differently. Because we can get them connected to the cloud. This technology is out there. It's available today. We just need somebody to do it. So remember, those 3 things that I talked about. It's all about the opportunity, how we're going to do it, and who's going to do it. So going back to the data for a second. Why did we care so much about the data in that application? Data has become one of the most valuable assets to the enterprise today. If you ask anybody, it's just like solving any other problem. How fast can I get information on what the problem is so I can figure out how to solve it? It's all about rapid acceleration of insight into business processes. That's what we're talking about. I know that sounds like a lot of jargon, but think about it. If you have visibility into what's breaking on your system or an opportunity to make it better, you're not going to make that decision to seek lower costs or increase profit. Everybody wants to stay in business and keep their business running. That's the data economy we hear about. You might have heard one of those buzzwords somewhere before. So what's the big opportunity that I'm talking about here? And I'm not talking about just dollars and cents revenue opportunity, although there's obviously significant revenue opportunity there. What we're talking about is bridging the physical world and the digital world. All that stuff out there, the billions of things that was never designed to connect to the Internet of Things. What happens if we start connecting it? Because right now it's not connected. Think about all the sensors, the relays, the circuits, the transmitters, the closed-loop control systems we've been shipping for decades. Think about how far back electricity was invented. Our opportunity is to cloud-enable this stuff and get access to the data. Now, to demonstrate what I'm talking about there, think about some stuff that's happened in the real world in the past few years. We've all seen the oil rigs off the coast of California, Florida, they're all over the place. Does anybody remember the one that went down in Florida a few years ago? You know what happened there? It caught on fire and it burned to the bottom of the ocean. And we dumped a ton of oil into the ocean. We completely screwed up the environment for a number of years. So that's one. What if we had an IoT application looking at data on that particular rig, figuring out, is a problem about to happen? Is there something I can do to avoid this thing catching on fire? Think about manufacturing. Are there opportunities to reduce waste, to reduce cost in manufacturing? Can we make manufacturing in the United States more competitive again? You know what that might mean if we were more competitive as manufacturers? That might mean more jobs, bringing jobs back to America. That could be a benefit. What if we took an IoT application and put it on there and figured out how to do that? Now, go back to our legacy infrastructure. All the stuff that's out there, our power distribution systems, our water distribution systems. Does anybody remember the story in the news lately about lots of people in Michigan getting sick from lead poisoning from a water system? What if we had an IoT application hanging out up on the cloud, looking at that system, figuring out there's lead in the water, shut it down right now? How many people wouldn't have gotten sick? How many kids wouldn't have gotten sick? Those are the applications I'm talking about. That's the opportunity I'm talking about. Sure, there's a lot of money to be made in these types of things, but there's an opportunity to really improve our society and the way we do things. That's what I'm after. That's why I'm passionate about this stuff. So, if this was an easy problem to solve, someone would have solved it a long time ago. You know, the smart guys at IBM would have typed the problem into Watson, it would have done some number crunching, figured this out, and spit out exactly what we're supposed to do. But obviously that hasn't happened yet because it's a significant challenge. So let's talk about exactly what that challenge is so we can try to get our head around it. Remember, the Internet of Things consumes data. It is a data economy. It runs on data. It needs data to operate. If all these systems are out there but we don't have access to them, how do we get the data and how do we make up valuable applications? I've done a lot of research on this, probably more than my boss wants me to have done, but I've boiled it down to several problems. The biggest I've seen, and the reason it's a big problem is because it's a human problem, is that two very different groups inside most businesses are going to have to work together. They're two very different groups because they have different cultures, they have different business objectives in supporting the business that they work for, and they use totally different technology designed not to talk to each other at all. So who am I talking about there? The operational technology group and the information technology group. So who are these people? On the operational technology group, this is where physical value creation starts. This is our manufacturing process. These are our manufacturing lines. These folks are typically dealing with legacy hardware, legacy software. It's legacy because it's reliable, it works, it's been installed for years. Now what does that mean? That means things don't change very often, which means some of these people can be slightly risk averse or resistant to change. They program their systems in something called ladder logic or function block. It goes back to the days of relay control logic. Invented a long time ago, 30, 40, 50 years. Remember, technology doesn't change very often here. So the hardware's got a long life, but that means it costs a fortune to buy new stuff. Again, supporting that, the hardware never changes things. This stuff communicates in the physical world using signals like analog current. So it's actually a physical electrical signal that we're trying to communicate, like the level of a float sensor or something like that. That's all the sensors out there that people are talking about today communicate, physical signals. Now, think about the systems that are there, the sensors, the motors, the pumps. All of that stuff is designed and built around an application to solve a problem, which means that a lot of the technology that's rolled out in these scenarios is application-specific technology. If you've never heard that term before, let me translate it for you real quick. That means it's often proprietary and extremely difficult to interface to different systems. So think about that group. Things don't change very often. Proprietary closed technology. Great people though. I work in that world right now. Let's contrast them with the information technology side of the enterprise. These folks are concerned about data management. It is all about data management. I want access to the data. I need to move the data. How fast can I move the data so that I can analyze the data? So their technology, they want to be as competitive as possible. How fast can we change that technology to make it better? These are the guys that are slamming out servers and slamming in new servers because they're 10 times faster than the old server. That gives me a competitive advantage. I can analyze data much quicker. So along that same story of quick, fast, rapid change, they use things like RESTful APIs, JavaScript, Node.js, Node-RED to quickly prototype and throw together their applications. Typically, these guys know about things like low-cost pies. They'll do some development on that, and they'll ramp it up to a system that exists in the cloud because it's reliable up there. It's backed up. These systems use open protocols. Who here doesn't love an RFC-compliant protocol? Maybe everybody doesn't know what that is, but that's a standard protocol that everybody knows how to use. Stuff like TCP/IP. You go home, your router, how do you talk to your router? It's got an IP address. It's an open protocol. That's why we use it. Things like HTTPS, that's how we interface with web servers, and MQTT to send data across the networks. This is where our web servers, our databases, our routers, our switches, our network telecommunications infrastructure lives. So look at these two groups, totally different. These guys are changing all the time. Those guys seldomly change. Two totally different types of technology. One is a closed system that's designed not to be messed with. One is an open system that's designed for updates and upgrade paths. They're in a constant state of change. So the question is, and remember, this is a human problem. That's why I think it's the most challenging to solve. The question is, how do we get them to bridge the gap? How do we get all that tech that's available on the data management side? Because remember, we're trying to get to the data. We're trying to access the data. How do we make all that data that these physical sensors and all the stuff that's already out there, how do we make it available to our big data systems? Because it's all about that physical digital gap and bridging that gap. We've got to make the signals of the physical world, the voltages, the currents, the data. That's our data, our sensor level data. We've got to make that information available to the cloud enable that stuff. So this is where I think, going back to what I said earlier, the three things, developers, this is where I think they're going to come into play. Because developers, like DevOps people, full stack developers, people mess around on Raspberry Pis or Arduino boards, they know how to take a physical signal on that board and post its value to an HTTP site, to a web server. That's what we're doing. Don't overcomplicate what we're trying to accomplish here. We're taking something from the physical world, an analog signal, and converting it into a digital information bit byte value and pushing it up to the cloud. That's what we're trying to do. That's where our developers come into play. That's why they're going to be the ones to solve this problem, at least from my perspective. So when they actually do solve this problem, and I finally get them on board, which is going to be a great day, and we've got this connectivity, and our sensors are talking to each other, and our systems are talking to each other, what is that going to cost us, and what is that going to look like, right? It's going to be awesome. It's going to be an amazing world at that point in time. We're going to have IP camera-enabled refrigerators in every house. Well, what does that look like? So as we start connecting these billions and billions and billions and billions of things that are out there, what's going to happen? They're going to start generating data, because that's what we want. We want that data. We want to get that data, analyze it, solve problems, figure stuff out. So let's go back in time again with me real quick. To the dawn of the internet. I was a kid, 56K modems. That was my window into the internet that we knew about at that time. Websites were coming online. I was jazzed about it. I was a little kid, so I could hop online and figure out what's the fastest remote controlled car right now? What's the best mountain bike to buy so that I'm way cooler than my friends? And I wanted to do that. And all that data was out there and available, but I had a tiny little pipe, a 56K modem, to get out there and get the data. It was maddening. I don't know if you guys remember trying to download a song back then, but you get about 3 seconds of the song, and then what would you see? You would see buffering, buffering, buffering across your screen. Everybody in here has had that problem. Maybe with your Netflix today or your YouTube, we're buffering, buffering, buffering. So go back to our billions of things. As we start rolling this stuff out and connecting things to the internet, that is a ton of data. So you'll notice up there it's a problem. Big data gets coined a lot as a really neat thing and a really neat concept, but you know what it is right now? As far as I'm concerned, it's a problem that needs to be solved for us to get to where we want to go. Connectivity is just the first step. The big data's got to be dealt with. I don't want all that stuff clogging up my Netflix, making me not be able to watch the shows I like. Come on, we can figure this out. So I think I have a solution to this problem. And this comes from the work I've done in the controls world. You know those closed loop control systems we talked about, where we're actually aggregating all those sensors and pulling in all that data? What if, instead of, say, let's look at like an industrial refrigeration application like at Costco. We're monitoring the temperature in the refrigeration system. Now, a control system is very accurate. It's all about timing. So it's monitoring that temperature every, let's be generous and say 250 milliseconds. We're checking that temperature. Is the temperature there? Is the temperature there? If not, go back to our control system. What does it do? What does it do? It sets an output to change the temperature in the refrigerator. So it's constantly checking, 250 milliseconds, 250 milliseconds. Now the question is, do we need to send that value, that 250 millisecond value, up to the cloud every 250 milliseconds? Why wouldn't we just take a little bit of computer smarts, a little bit of processing power, and push it down into that control system? So maybe it could aggregate and average that value over a certain amount of time. Maybe it only needs to be pushed up there every half hour, every hour, maybe once a day, maybe once a week, who knows? But that's where that term edge computing and edge processing comes into play. You got to push that intelligence down there, because we don't want to flood the entire internet with a bunch of erroneous data that we don't really need. So that's edge computing, edge processing, and I think it's going to solve the big data problem. When you hear people talk about big data, if they know what they're talking about, they'll refer to it as a problem. All right, so let's go back to these places we'd like to start putting control systems, like our oil rig that sank. What is the control world like? It's real time. Things happen right now. Lickety split. It's just like that industrial refrigeration system. We're watching every 250 milliseconds. Control signals have to get there right now. We can't wait for them. We can't have that buffering, buffering, buffering problem. So when we roll out tech, IoT tech, to these applications, we can't think about the systems down at that edge level having to interrogate the internet to find out what they should do. For example, When the oil rig catches on fire, don't check with the internet. Don't see if now's a good time to turn out the fire. Just put out the fire. So there's always going to be a need for some kind of control down at the edge, some kind of intelligence down at the edge where we're aggregating the data where we can do real-time control. Because these are mission-critical applications. This is life and death stuff. We're talking about people's water systems, people's electrical systems. We're talking about our energy sources like wind turbines and oil rigs out here. It's very important stuff. All right, so remember the three things: the opportunity, how we're going to do it, and who's going to do it. So I spent a lot of time trying to put a number on this opportunity because I'm a numbers guy. I like to know exactly what the value is before I get involved. So I tried to figure out how many things are out there in the world today that we could benefit from connecting to the Internet of Things. Because then I got an idea of, man, this is a really good idea, or this is going to take a lot of work and I don't want to deal with it, which is kind of why I'm making the point. I don't want to dissuade you from the opportunity here. So I did a ton of research. I looked through all these analyst databases. I could not find a clear, concise number of things that were out there. People had ideas. A lot of times the idea was, it's big, right? Our big data, which means we don't really know, but there's a ton of stuff out there. So I started thinking about it. My company's in this space, right? We build those control systems that aren't connected right now to the Internet of Things. We build these I/O modules too. They're the little cards you see on the right-hand side of the rack. Now, we've been in business for about 40 years, and I promise you this is not a pitch on my company, but I do have an awesome opportunity to talk to you about called Amway, or Herbalife, right after the show, right after the presentation. So, going back to my I/O modules, remember that's input-output. I'm taking input from a sensor, and I'm setting an output on a real live device like a pump. So in 40 years, we've shipped 100 million of these modules. Now, I want that number to sink in, so think about it for a second. 100 million of these modules. That's where we're going to build our base for the opportunity. That's where we start. Now, my company, we have competitors just like any other company. We're kind of the small guy in the market. You know, we have competitors, but we compete, and we compete very well with them. But you know who they are? They're giant juggernaut companies. Rockwell, Siemens, General Electric, Schneider, companies that have been around longer than my company. So what's my point? Go back to the 100 million modules. We've shipped 100 million. How many have those folks shipped? How long have they been in business? You know, 80 years, 60 years? How many modules have they shipped in that amount of time? That starts to give you some idea of the number of things that are out there. No, I can't put a number on it for you, but there's a lot of stuff out there right now. So going back to the question, if we started connecting all those billions of things out there, what kind of problems could we solve? What could we actually do with that? All right, so here's my grand plan, my grand solution. Here's where I tell you how I think we're going to do this and what we need to do it. The first problem, that convergence problem, getting the two groups to work together. It's a significant problem because it's a human problem. We're dealing with people here. People that don't like each other. That's why the two guys are yelling at each other, because I've been in both these camps before. I've been on the OT side, I've been on the IT side, the ops technology side, the information technology side. You know, the ops guy, he's risk averse, he connects his system to the network, he's trying to get to know something new, and then the IT guy freaks out on him and says, whoa, I haven't run a penetration test or a security audit against that thing. What are you doing connecting to my network? And it's the same thing on the other side. Don't touch my control system because somebody might die. So totally different cultures, different objectives. Remember that, they're trying to accomplish a different task. So how do we bring two different groups of people together? How do you make a friend? That's the easy question. How do you make a friend? You find some common ground. Now, like I said, I've been on both sides of the enterprise here. You know what the commonality is between the two groups? It's uptime, right? Because the IT guy's got to keep his website up all the time. Think about it. If you're a consumer and you're looking for a product or you're looking for a service, what do? You get online, you Google it. If the product's website isn't up, what do you immediately know? You don't even have to think about it. There's no website, what do you immediately know about the product? If we can't keep a website up, what's the product or the service going to be like? It's the same thing on the OT side, except it's possibly a little more drastic. If his system goes down, his closed loop control system, the fire control system, whatever it is, you know what happens there? People might die. That's a pretty serious problem. So start with uptime. But that's just the beginning, because remember, we want the data. It's all about getting the data from those physical assets out there that are already there and existing, generating data. It's all about getting their data into the IT systems that these folks run. If we have one common business goal, one common business objective to run everything up under, we might be able to get there at some point. Because remember, the enterprise will demand it. Businesses seek profit. They want to try to cut costs. It's going to happen eventually. Both groups might as well get on board at this point, and I would start with uptime. But remember, it's all about the data. So hopefully there's some developers in the audience today, and you might be thinking to yourselves, I'll prototype an application really quick, I'll throw it together with a Raspberry Pi, which you could because Raspberry Pis are awesome for prototyping, and they already have this kind of stuff built into them. They're easy to learn on. They were designed for students to learn how to program something with. They're cheap, they are available, they've got GPIO built into them, 3.3 volt logic pins, so maybe I can pull in some of that sensor data. It's got an SD card for storage. So I can put my favorite Linux distribution on there. It's already got things like Node.js and JavaScript. I can build my application there. Let's talk about why we might not want to use those systems in this type of environment. So first thing you should notice, do you see the flamethrowers coming out of this thing? That's a lot of fire. That's where we're going to put the Pis and the Arduino boards and all those other things that we're talking about developing our application on. Now remember, these are vicious and frightening places. Very tough people work in these environments because it's hard to survive there. It gets extremely hot or extremely cold. Things get dropped, things get hit, things melt, things freeze. When operators get upset about things aren't working, they might run something over. It's happened, I've seen it. Remember, the industrial world is using GPIO. This is our infrastructure we're talking about. We're not using 3.3 volt logic. We're switching 400 volts AC, stuff that will literally kill you if you touch it. GPIO is not going to work for that kind of application. So in these applications where it's all about mission critical, we built things in like IO channel isolation. Because if one thing attached to the control system pops or explodes, we can't have it taking out the rest of the stuff. So it stops at that one specific IO channel, that one thing. It doesn't go to the rest of the system and bring it down. And then the control system is still up and running. We're just waiting to replace that one little thing. EMI resistance. We're moving around a ton of electricity. Think about the magnetic interference that's going to be in these environments. And power loss and file system recovery. Can you guarantee that those systems powered down at any random moment are going to boot right back up and start doing exactly what they were supposed to be doing? Or is there some doubt there? So remember, things have to come right back up and actually start working. So my suggestion, I would start prototyping stuff on Raspberry Pis because that's what they were designed to do on your Arduino boards. But I would try to keep in mind that at some point in time, you might put a flamethrower to it. So make sure it's designed to actually work in that environment and operate in that environment. Because what's the real cost, like we talked about? These are mission critical, life-saving applications. That oil rig, if it catches on fire, think about it. What's the delta between the cost of one of these little boards, putting it in these environments, and the cost of sinking that oil rig to the bottom of the ocean? At a minimum, it's human life and very expensive equipment being destroyed. So like I said, prototype on whatever platform you want, and then ramp it up to something that can survive actually at the edge. So kind of recapping what I think we need there. There's a system, some kind of system we need. It's got to be industrially hardened. It's got to be able to survive the flamethrower test, right? It's going to need to be able to bridge that physical and digital gap, which means it's got to be able to translate voltages and current into languages that the Internet of Things understands. So we take that physical signal, an analog input or analog output, and we make it available in the digital world, up in the cloud, to cloud-based systems. It's got to be able to survive that harsh environment we talked about. And it's going to need a ton of physical I/O because there's a ton of stuff out there. Sensors, relays, actuators, all the stuff we've been shipping for decades and decades. The most important thing I think it's going to need, though, and that's how I'm going to get the developers on board, it's going to need IoT communication and programming capabilities. We don't need any more application-specific tech. I'm tired of it. It's ridiculous. Think about the internet and how fast it rolled out. It rolled out because we were all speaking the same protocol. We were all speaking TCP/IP. Let's get on the same page. And let's do the same thing with our development tools too. Forget about some proprietary development environment. There's a ton of great stuff out there right now. Node.js, JavaScript, HTTPS protocols. All this stuff is out there. RESTful APIs. All the stuff that our IoT developers are using right now, if we could port that over to our legacy equipment, what kind of value could we get out of the data? So let me recap. wrap it up for you. The market opportunity is huge, and the opportunity is not just dollars and cents. We can actually make a difference here and improve the way things work in our life, our society, our water systems, our electrical systems. The tools are out there today to start prototyping and putting these applications together. We can do it right now. The only thing we're missing are the developers. It is all about the developers and getting their talent attached to this problem and figuring it out. So thank you very much. I enjoyed talking to all of you today. If there are any questions, I've got a microphone. Any questions? Oh, I need to give you the microphone, sorry. I was told very clearly that this is very important.
Thank you very much for the excellent presentations. I enjoyed it thoroughly. So I have a couple of questions. The first question is when it comes to the connecting these devices to the cloud, you have security in questions, right? I mean, security model.
Absolutely. And that, you know, I told you I've spent some time in the OT world. These folks, because remember, their systems are designed to be closed off. They're designed to perform a task, not communicate with other systems. So security, nobody thought of it. But now we're start talking about connecting this stuff. That's where, again, the IoT protocols are going to have to get built into that hardware. So you're going to need things like SSL and SSH, not SSH necessarily, but SSL and authentication. All that stuff's going to have to get pushed down there. I know in the OT space, I don't know if anybody here heard about that, but there was a nuclear reactor that got hacked at some point in time. Suddenly that brought the operational technology people into an understanding. There's a significant risk out there. We're talking about blowing up nuclear power plants. So there definitely does need to be security built in to the systems that we put at the edge. And that's going to be up to industry to figure out how we're doing that today. But I can tell you, the product that they used in that wind turbine application, it already came with SSL encryption built into it because it's a Linux system. The Linux box was designed to survive on the internet. How did it start off? It was a server.
Sure. Thank you. And my second question is, interestingly talked about, these are all low-end sensors, you know, analog or digital, one-wire or two-wire sensors. Yep. So we are working with the 5G environment on the other side, you know. Mm-hmm. So do you think these sensors are really, you know, capable of working in this environment? Because there's a 6LoWPAN, Bluetooth, those things definitely can work. But when you connect to the 5G, whether is there a appropriate working model there or anything in between we need to include to enhance the speed there?
To enhance the speed of the communication from the sensors. Right. That's what you're talking about.
Thank you.
You know, in the architecture that I'm thinking about, I think, sure, there's a hardware problem here, but I think there's a software problem too. I think right now all the existing infrastructure out there, because it wasn't designed to talk like this, it doesn't have those capabilities built into it. So in our world, how I would answer that question for connecting sensors like that, wireless sensors, I would just design a new module and pop a new module on that I/O rack that knew how to speak those protocols and start getting that data. And then again, at some point in time, all that data's got to be aggregated somewhere and filtered out and put together. And that's where I think those edge systems are going to come into play.
Thank you.
Mm-hmm. Any other questions? Anybody? Going once? Going twice? Go ahead. Oh, yeah, that'd be great. Thank you.
Thanks for the presentation. Who built the smart turbine or like? Did you mention the name?
I did not.
Oh, okay. I know. I think you.
But I should because they're a great company. They're named SCADA Solutions. They're a Southern California-based company, and this guy that put this system together is incredibly passionate about green solutions. And he didn't necessarily have much of a PLC or industrial automation background, but he was able to take some hardware. You know, he understood database programming and Linux programming and put a solution together.
Oh, okay.
So SCADA Solutions, SCADA Solutions.
Oh, great. Okay, because I do some projects. Well, I'm at Lawrence Berkeley Lab, Department of Energy. So
sure.
We do a lot of projects where we're trying to understand how energy is used in buildings. So it's, you know, we have, and then I also now do like we have. I work on a project with these micro phase measurement units on the grid. So yeah, I can relate to a lot of what you're.
Yeah, we can take all of the sensor data that you're collecting and aggregate. Well, We have a booth here. You can stop by and check out the booth. We've got a sample. You might have seen it. We're the turbine company out there. We've got the big white windmill spinning around. If you haven't seen it, check it out. It's pretty cool. We'll show you the tech that we actually use to put it all together. So
All right,
feel
great.
free. Sure.
Thank you.
Another one over there. Let me grab the mic from her. Thanks. There you go.
Thank you.
Uh-huh.
Great presentation.
Thank you.
For those that don't know, SCADA means supervisory control and data acquisition.
Supervisory control and data acquisition. That's
Does
right.
that sound familiar?
No, and I wouldn't think that the majority of the people here know about that because that's an OT technology.
Understood, but just take the words.
Mm-hmm.
Do the words sound familiar? I mean, you control things, you supervise things,
Sure.
you acquire data.
That's what we're trying to get to.
And I think what's going to happen here is the old technology was it's almost like 30, 40 years ago, where the OT people are using minis and mainframes, the digital equipment, the Burrows, the Sperry's.
You've got it.
And we are coming along with the PCs, which to them look largely useless.
That's right.
Okay? But in time, the PCs took over the infrastructure, and there is no more mainframe mini computer technology anymore.
You know, I've thought about that a lot, and I would counter that point with, if you think about where we're going with the cloud and the hosted servers, I can't wait to switch to a Chromebook and get rid of Windows. You know what I'm talking? So I think my point is, I think it's going back to that, almost like that mainframe architecture.
Well, that pendulum has always swung. I mean,
Sure.
History rhymes, and we never seem to be able to stop in the middle and take care of it all and just
Figure it
live
out.
a good life.
Yeah.
Here's an issue that I'm concerned with. I actually, for the last 5 years, have been working for a company that makes sure people have safe drinking water. In this case, they're dealing with situations where a contractor built a subdivision where it was too expensive to bring city water, so the subdivision, he drilled a well.
Sure.
Okay, well, all of a sudden he finds himself in the utility business. He doesn't want to be in the utility business, so he turns it over to the homeowner association. The homeowner association, they end up thinking, oh, this is excellent, water should be free. Well, as a result, eventually problems start to happen. The homeowner association didn't save money. Now the feds have to roll in with a drinking water program. Well, the challenge here was these neighborhoods, after they've run across the problem, there is no money, and yet they still need automation. They still got to submit reports. They've got to pay an operator. Somebody has to be checking it frequently. Well, the people I went to work for, named Northern Utility Services, they operate about 70 of these systems and have one other competitor in Anchorage that operates approximately 70 more, within what theoretically should have been the jurisdiction of the city water system.
Sure.
What do they do for automation? Well, the answer was, they should buy an Allen Bradley or a Siemens or whatever. Well, guess what? IBM once predicted there might be 50 companies in the world that might need a computer, and it was based on the price.
Right.
The same thing's happening here. I ended up pulling together a solution that's an Odroid plus an Arduino that links to all the old sensors. We can tell remotely what's going on. It's working. It's not industrially hardened,
Sure.
but it's there and it's functional, and it cost them $500.
Sure.
So there is still a place underneath where we need to come up with not the Allen Bradley equivalents, but literally the PC equivalents as opposed to the Allen Bradleys of the day.
All right, so the presentation's over.